Hello, friends. I'm Ashish Darbari, founder and CEO of Maximize. To our new listeners, welcome, and to our old ones, welcome back. I've got a very interesting person in-house today, and I say interesting because he's doing a lot of new stuff that a lot of us may not be familiar with, and it has to do with design, it has to do with languages, and it has to do with verification. So, friends, I have today Steve Hoover, CEO of Redwood EDA. Hi, Steve.
Hi, Ashish. Yeah, thanks for having me on your podcast.
Oh, pleasure, man. We've been trying to get you for some time, and I'm so thankful that you could find some time. And
yeah, it's been nice. It's been nice talking with you and learning about what you're up to. I'm really excited about it.
Great. So, Steve, before we get into what you're doing, I want to just take a step back and understand a little bit about your background, about some of the fascinating things you've been doing. What was your journey? Where were you born? Just so that we get an idea, why the hell are you doing what you're doing?
What makes me tick? Yeah. Well, I mean, my background, I'll try to be brief about it. It's not the most exciting thing we can talk about today. It's a pretty typical engineering background. You know, I grew up with interest in math and science and was sort of leaning toward engineering before I knew what the word meant. You know, in school, I think I really ended up focusing on computer engineering because I realized that no matter what my focus was in school, I would end up programming. I would end up using computers, and I wanted to understand what it was that I was using. So that remained my focus. I basically escaped out of a PhD program at the University of Illinois with a master's degree.
I see.
And went to digital equipment, working on alpha microprocessors. And, you know, that was really exciting working on the DEC alpha.
Yes.
You know, very much focused on performance, pushing the envelope. Who cares about power? Well, apparently the industry does. But, and then through acquisitions to Compaq and to Intel.
Right.
So most of my career was with Intel.
I see.
And
so where were you based? Where were you based in Intel?
So I've been on the East Coast, Intel, Hudson, Massachusetts.
Oh, I see. Cool.
And kind of jumped from Hudson to Shrewsbury with the Compaq acquisition, and then right back to where I was at Intel, back in the same building in Hudson, Massachusetts, which was a rather, I don't know, felt like a regression going back to the same site I was at several years earlier. But so I kind of went from CPU core outward into memory interface, cache coherence logic, system logic.
Right.
The last role that I had with Intel was as the lead logic design of one of their high performance switches. You know, Intel's been getting into network architecture and high performance computing. With the acquisitions of Cray and QLogic. So I worked with those teams.
Right. So most of your career has been very much in the area of microprocessors. I mean, I remember when I was a graduate.
I started out in verification for about 5 years and then focused on logic design, microarchitecture.
Right. I think when I was coming out of school and going into college and so on, everybody just talked about hardware as a microprocessor, and that was the only thing that people thought was driving a chip. But now we have GPUs, we have videos, we have special networking in designs. But it's fair to say that a lot of early innovation, and I mean early in the sense of last 3 decades or so, has been predominantly dominated by mobile computing and videos and GPUs and the like. But anything before that has been predominantly microprocessors, whether it was the IBM or
CPUs.
The Intel.
And in school, you know, that's what we learn. And it's a good focus for education, but I think a lot of students don't realize how much more there is to microarchitecture than just CPU architecture.
Oh, yeah. Absolutely. I didn't even hear the word microarchitecture in my undergraduate days. So, Steve, how long have you been with the industry before you actually moved into a startup?
I was in industry close to 20 years before I kind of left that and started doing my own thing. I mean, I think what motivated, me leaving and starting up Redwood EDA was I mean, even in the early stages of my career, I looked at the tools that were available and how people did design, and there was so much tedium in the process. And I, even at the beginning, it seemed kind of ridiculous that the tools weren't more capable. And, almost 20 years later in my career, we're fundamentally using all the same tools, the same methodology. I had learned a lot about how design should be done. And just over the years, it became more and more frustrating and more like I was working on the wrong side of the problem.
That's a very interesting comment. I'm not sure I fully agree with you because I'm coming at it from a formal verification point of view. But let's...
Yeah, and I think, in formal, the world has evolved quite substantially.
So you saying...
and I don't mean to... Yeah, I mean, these are broad brushstrokes,
Yeah,
right?
of course. But these are perspectives of what you're talking about. And I think what you're saying is in terms of design synthesis, power estimation, and primarily...
Yeah, I mean... Tools have incrementally evolved. Right. I mean, the biggest thing is we've scaled significantly.
Yeah, that's right.
But the methodologies fundamentally haven't changed that much, and they're not keeping pace with the scaling of technology.
That's right. That I agree with you.
And I know you're very focused on formal methods and abstraction, and those are the keys to dealing with the complexity, crisis, I'll say, that we face with the scaling that Moore's law has pushed upon us, right?
So, Steve, takes a lot of guts to leave a well-paid job and actually start your own enterprise.
Yeah, there's a fine line between guts and stupidity, but thank you.
I think we're all part of the same side, right? So I left a well-paid job to start my own entity. So what made you actually say enough is enough, let me now go and do something of your own? Was there a specific trigger or...
I think it was that. It was the... I guess for many years before that, I knew that I wanted to focus on design tools. And even as a logic designer, I would often innovate tools and methodologies within that role. But I wanted that to be my primary role because I saw so much opportunity and so much need there. But the idea of going and working for one of the big EDA vendors didn't feel like the right path to having an impact on the world. And it's not that I necessarily want to be off on my own, driving things on my own without the support of a large company behind me. But I just didn't see that large company that was the right place to foster innovation and change the industry.
Yeah, that is a fair point. As a startup, we do get a lot of freedom to innovate. So let's talk.
There's definitely that.
So let's talk about that freedom side of it. Yeah. So you and I've spoken about this before, but for the sake of our listeners, a lot of your business is about transactional Verilog, right? TL-Verilog. That's what you're basically proposing as a game changer for improving design efficiency and verification efficiency and synthesis, right? All three side of it.
So that's right. It's really pretty holistic, and it's about the methodology. The language, transaction level Verilog, is a manifestation of that.
Right.
An incremental path to adoption deriving from Verilog.
So before we go into what is it, tell me why you thought TL-Verilog is something you need. What was it that
you never want to innovate new language because you're taking on a whole new set of challenges to shift away from the industry norms. But System Verilog really doesn't have the fundamental basis to support the next level of abstraction, the next level of design methodology. So there isn't really a choice but to crack open the language and start introducing new fundamentals. And the idea of layering on top of Verilog, of course, is to make that as painless as possible, to make it a proper language extension so you're not throwing anything away. You're only adding capabilities, and by incrementally adding capabilities, you obviate the need for some of the legacy functionality of the underlying language.
So this is a very fair point. I talked to Simon Davidman a few weeks ago, and he's had a profound impact on the design of Verilog and System Verilog languages. And one thing that he said to me, I remember quite vividly, saying, no language is perfect. None of these two are perfect either. They have their shortcomings, but people should not just give up on these and go and invent completely new languages. They should add value and fill up those shortcomings. And I think what you're saying is TL-Verilog is achieving that. And potentially it may actually go in the standard of Verilog at some point. Am I?
Yeah, I certainly hope, that it does. I think at this stage in its development, it's important that it remains sort of independent. I think there's a lot of value in staying true to the vision and driving it in a sort of a small scale before it takes on the overheads associated with the standards body and all those sorts of things. So I think it's following a natural progression. But hopefully, as it becomes more broadly used and accepted, certainly it needs to go through those steps.
So I'm not sure we still know why you made the choice of going down the path of transactional Verilog. So what is it that you're solving? What is the exact problem? Yeah.
Right. I mean, fundamentally, as you and I have talked about, abstraction is key.
Yeah.
And this is really about incorporating abstraction into the design process in a productive way. And it's about the design process, not just how do we express a model. Models are always changing, and the capabilities have a lot to do with easing our ability to make modifications to the design without breaking it. So if I can sort of make one high-level statement about what fundamentally is transaction-level design, in contrast to existing methodologies, right? We have the industry, obviously RTL is still predominant, and high-level synthesis, for the most part, is the contender. TL-Verilog fits nicely in the middle, sort of a best of both.
I see.
Where you're not giving up control to high-level logic synthesis to make decisions about your design. You, as a designer, still have control at the register transfer level. But you're able to incorporate abstraction, abstract context into your modeling, so you can benefit from that abstract context. And it's really about bridging abstraction levels, right? As our designs scale and just become more and more complex, we can't keep thinking about, okay, we need to model at this level and we need to model at this level. We need to bridge the gap between these two models. And our world's just gotten exponentially more complicated. We need another model up here and to bridge that gap. We need to focus on the mechanisms that are going to help us bridge models at different levels of abstraction and incrementally attack the problem of building these very complex systems and verifying these very complex systems.
So what you're saying is that high-level synthesis is not going to disappear. You're not upset about high-level synthesis being used. In fact, what you're saying is there is value, and there is value in the downstream Verilog compiled models, as it were. But you're saying somewhere in the middle is where a lot of things get missed because we leave too much in the hands of a high-level synthesizer, and we lose the ability to apply human-based, abstraction-driven, transactional way of building the designs.
Yeah, there's definitely value in high-level synthesis. The capabilities of high-level synthesis tools are really quite phenomenal. The thing that I am upset about with high-level synthesis is the language choice. Choosing C-based modeling as the foundation for modeling hardware is just absurd. And I've even talked with some of the folks that were involved in the early decision-making of high-level synthesis. And nobody that I've talked with, they've all said, yeah, we weren't really comfortable with that choice. We didn't like it either, but we didn't want to invent new language.
Right.
And that's what I'm doing. And right now, my language is layered on top of RTL as the predominant methodology. But certainly, ideally, all of those valuable capabilities that exist within high-level synthesis flows would be absorbed into this methodology now with a stronger foundation for a language that really is meant for hardware.
So I get it. I get it why you believe there is a gap in the middle. Now, what are you saying is, if I wrote a program in TL-Verilog, you have a compiler that can turn this into vanilla Verilog?
Your TL-Verilog model actually is not doing any high-level synthesis. So my compilation tool, Sandpiper, is actually a code translation tool. It's translating your TL-Verilog language constructs to Verilog or system Verilog. And it's but everything about your register transfer level is explicit. It's just explicit in a way that's more compact and easier to maintain. you would sort of think that by having a model that has all the same level of detail, but the addition of this higher level information about the model, higher level of abstraction, that since you're adding more to the model, it must be a larger code base. But actually what happens is with this higher level context, so things like proper language constructs for a pipeline and for a transaction, that context gives you context to specify the register transfer level much more concisely. And the modeling actually, if you just do a direct translation of a Verilog design and translate it over to TL-Verilog, it generally is about half the size.
So this is fantastic because I'm a big fan of compact code and abstraction. And
yeah, there's a lot of evidence that bugs are proportional
to the
code size.
Lines. Now tell me something about how do you believe TL-Verilog fits in with BlueSpec and Chisel, two languages that have been used more recently in the context of RISC-V, but BlueSpec has been around for much longer. And what are your thoughts on these two versus TL-Verilog?
Yeah, I mean, BlueSpec, and I know a lot of the folks that were responsible for BlueSpec. They're a great team of folks. And BlueSpec is probably the closest analogy to what I'm doing with transaction level Verilog.
Nice. Okay.
It fits into the process the same way. It's more abstract modeling that compiles down to Verilog. Some of the key differences, the transaction level Verilog, just from a pragmatic standpoint, it's producing code that is readable, much more readable and maintainable than any other language that's outputting Verilog. Your source code, it's actually producing a file that's line for line compatible with the TL-Verilog source. And then it's producing another Verilog output that's things that are correct by construction, which include flip-flops, signal declarations, clock gating logic.
So correct by construction is a claim made by BlueSpec and Chisel. And what are the key ways?
And they certainly are. I have no objection to that claim. They are correct by construction. The point that I'm getting at is that the correct by construction content is sort of off to the side, and the errors that you get downstream are going to be in this Verilog file that's line for line compatible with your source code. So if downstream you get an error on line 89 of your source code, you turn to line 89 in your TL-Verilog source code. It's the same logic expression.
So debugging and code maintainability are two key features that
it's very important.
Yeah,
right. And that's where the challenge comes into introducing layered languages. When you add a new layer into the process, it's a layer of obscurity versus downstream.
So did you at any point consider working with the BlueSpec team to incorporate a lot of your transactional Verilog concepts into the main framework of BlueSpec?
Yeah, certainly thought about, BlueSpec has a lot of capabilities that are very nice. And I've certainly thought about, instead of layering, in fact, if I can step back for a second, the general methodology behind the tools that I've put in place is to be a layer on top of an RTL language. So they're not fundamentally specific to Verilog. The Verilog is the only implementation of that, the output. It's the only output that we can generate today. But the tools are structured so that we could fairly easily support VHDL if we wanted to do that, and other hardware description languages.
I was going to ask because just going back to Simon again, I think recently, 2 weeks ago, they published a paper with Phil Morby and Peter Flake, the whole history of Verilog being there. And I think in the abstract, I read that they say 80% of the world's semiconductor designs are built using Verilog. But, there is 20%, which is potentially high-level synthesis and VHDL. So anything you are doing would be relevant for VHDL users as well, right?
The tool support is not there today, but it's headed in the direction of being able to support layering on top of Verilog if there's enough motivation to implement that. It's not a very significant effort.
Right. So I remember talking to you some time ago, and we were looking at a few examples you were showing to me. And am I right in thinking that the most apt designs for TL-Verilog would be microprocessor-based designs, things that are pipelined and have...
So yeah, pipelining is certainly a very fundamental construct in TL-Verilog. I wouldn't say though that it's specific to microprocessors.
Nothing specific that is only, it's not limiting in that way, what you're saying. That it only
no, certainly not. And the value extends to any digital sequential logic sees similar benefits.
Okay.
The pipelining construct, it's supporting a type of modeling.
Yeah.
It's a type of timing abstract modeling.
Right.
And it gives you this property that you can easily retime logic without breaking functionality.
Yeah.
Pipeline, a CPU pipeline is a natural expression of a pipeline that can benefit from that.
Right.
There's also, even if your logic and things in your design are following different flows other than pipelines, that's where the transaction level modeling comes in, supporting transaction flows. And you get the same kinds of benefits there, being able to move logic along the flows that you're establishing.
So this sounds really interesting. So
bottom line is there's benefit across the board to any digital logic.
So I know you ran a course recently teaching RISC-V design using TL-Verilog, but how do we get about learning this? So what are the opportunities available, and are they, people have to pay for your courses, or are they free courses? What is the current status?
Yeah. So best way to learn about transaction level Verilog. So it's, I'm sure you're aware, it's not really feasible to create a business around language. It doesn't make for a very good elevator pitch. So, early on, starting Redwood EDA, and it's about productivity. It's not about language. And there are a lot of elements of productivity beyond the language itself. The language is just the, setting the stage. And then on top of that, there's been a lot of focus on building up a development environment, an IDE that supports transaction level Verilog and sort of builds in the abstractions that TL-Verilog offers throughout the IDE.
Okay.
So that's makerchip.com, and it's available to the world. Anybody can go to makerchip.com. There are some tutorials and so on to walk you through the different features of transactional.
So the language itself is free to learn, and people can license some of your tools if they were.
Yeah, my business model, which works out really well, I think, is basically if you're willing to do your hardware development for free, I'm willing to give you the tools for free. So Makerchip is free for open source hardware development, but we fuel that with commercial. I mean, obviously, Redwood EDA is a commercial entity. If you want to run these tools behind your corporate firewall on your proprietary code, you would pay for that.
Okay.
But I really see a lot of opportunities with the open source ecosystem, and I'm very interested in fueling that ecosystem with the Makerchip platform.
Right.
But back to your question about how do you learn about TL-Verilog? What are the training resources? Yeah, I did a training workshop with a guy named Kunal Ghosh, who does a lot of training in India.
Right.
And we did a really exciting workshop series. The students were just really enthusiastic about it. And I think it was a nice showcase for what you can do with TL-Verilog. So this workshop, there were 2 days where Kunal was just teaching general information about the RISC-V instruction set architecture and the standard tools like Spike for RISC-V. And then the remaining 3 days, I was teaching, just assuming no background in digital logic. So starting from logic gates, and then teaching TL-Verilog tools. Students jumped into Makerchip right away. It's easy to just jump in and start coding. So as soon as they learned what a logic gate was, they coded a logic gate and saw it in simulation.
I see.
And then within those 3 days, we had the students build their own RISC-V cores and simulate them.
Nice.
And, I think that's something that nobody's been able to do before. I mean, this is typically several college courses to get through learning digital logic and CPU microarchitecture and actually using Verilog to design a CPU core.
Awesome. No, this sounds really great. Compact, few days course that gets you hands-on, involved on the deep end. This is awesome.
Yeah, and I think, and for your listeners who are interested in that, feel free to reach out to me. We're going to do another run of that course very soon.
Nice, very nice. So people who are listening to us, if you fancy learning the next generation hardware design language, TL-Verilog, then Steve is here to help. And it's not very expensive either, right, Steve, to get on this course?
The course, I think, we haven't settled on the price yet for the second round. It'll go up a little bit, but it's certainly a reasonable price.
Sure. So they can get in touch with you. So let's change the gear a bit. I love formal methods. I'm into verification, and obviously I'm also passionate about design languages and such. And in my PhD, I had a look at designing a high-level type system to capture some regularity in circuits. So I can totally appreciate what you're trying to do and why you're trying to do. But in the real world that I work in, with people who are used to Verilog and VHDL and whatnot, they need verification done. And that's what we are kind of doing now. I'm trying to understand, how can verification benefit from TL-Verilog? And is there anything that formal verification users in the world could benefit from if the designs were designed in TL-Verilog? Because that would be quite a significant advantage for verification.
Yeah, I mean, I guess before I answer that, first I want to just say, how important it is, Ashish, what you're doing to promote understanding of formal methods. I think, formal verification needs to be a very important and fundamental part of the design process today. Certainly verification represents a very significant part of the design process, 70% perhaps. And if you're not solving verification problems, you're really not addressing the important problems. TL-Verilog, even though it's focused fundamentally on design, on incorporating abstraction into the design process to accelerate the design of your hardware, that the benefit of abstraction permeates from the design into the verification process. Existing verification methodologies, all layered on top of Verilog, focus on how do you do the verification modeling in more abstract ways and more beneficial ways, but they're still fundamentally attached to the same level of design, to the register transfer level of design, and that's the level of complexity that you need to address. With TL-Verilog, you're able to raise the abstraction level of the design itself, and it sort of creates a separation between the higher level transaction level design and then the details of how that's implemented. So, some of the detail in your model is correct by construction.
All right. Yeah.
And now that your model is a higher level of abstraction, right? You've cut off the base of the pyramid, right? If we look at complexity and the layers of models as a pyramid, the more detail you have, the wider you are, and then as you go up the pyramid, things exponentially actually get smaller and smaller. And if we cut off a layer at the base of that pyramid, we're cutting off a lot of the work, and that's what TL-Verilog does, right? It gets you to a higher level of abstraction that your verification models have to connect to and worry about. And by that, all sort of pie in the sky, high level arguments, but in general terms, you're simplifying the verification problem by simplifying the models themselves.
So I get that, but are you also able to then generate in the background assertions that guarantee that when these TL-Verilog models would be compiled down to Verilog, then those two models would have certain relationships between them? Is this something you're doing in the background? Could this be?
Yeah, and maybe I'll mention one thing in particular that exists to try to make this a little more concrete. I mean, it's hard to go into technical details in a podcast. It's not the right medium for that. But one particular sort of level of understanding that you have in a transaction level Verilog model that you don't have in Verilog is an understanding of when the circuits are doing something meaningful, right? Generally in a circuit, 90% of the time the circuit's just sitting idle, and the values might be propagating, the flip-flops might be toggling and whatnot, but it has no meaning. And RTL doesn't give you any way to convey that understanding.
Right.
Transaction level Verilog does.
Right.
And so that's additional information that you can utilize to essentially get assertion checking for free.
Right. Right.
So you want to make sure that you're not consuming these values that you
not
believe to be garbage.
Correct. That's really nice. And this is an area which I also picked up in our last chat. And I think this could be particularly beneficial for larger scale formal verification because, we're looking at verifying 32-bit cores or 64-bit cores. That's a lot of state. And as you said, for a lot of combinations that are non-interesting, we don't really care. We only care about transactions that are interesting, which are mapped to instructions in the sense of RISC-V, for example. So anything else is besides the point. And the tools should not be wasting time looking and scanning those states in a formal tool. And as a human being, maximize what we do is we come up with these invariants that actually express interesting relationships between interesting transactions and between different transactions. And trying to extract this from an architectural spec is easier, but getting it from a microarchitecture Verilog is a nightmare. And we often rely on human, readable specs, microarchitecture specs whenever they are available. But what you're saying to me is that if we create the abstraction layer at the design level slightly higher, then we can actually tap into that, and which is the nice thing about the framework that you're talking about. So I certainly see
there's
this more valuable.
There's certainly, assertions that you would tend to write in code today that check properties that you don't even have to check because they're below the level of abstraction that transaction level modeling is providing.
Yeah, you could still generate them and they could still be proven in the tool, and they might be very quick to prove because they're establishing behaviors that are well bounded in terms of number of cycles and so on. So Steve, let's talk about this open source side a bit. So you mentioned open source earlier and you said it has relevance to what you're doing. And there's a lot that's happening in the open source ecosystem right now. Where do you think you fit into this from a Redwood EDA point of view, and how?
Yeah, there's a lot of enthusiasm and excitement for open source. Certainly, RISC-V has fueled that. But I think what we're seeing with RISC-V is really tip of the iceberg, or I don't know. I guess when you see a tip of the iceberg, it's 10% of the iceberg. I think we're seeing 1% of the iceberg. I think what's below the surface here is really exciting, and I don't think that the silicon community has really picked up on what's about to happen with open source. And so let me kind of map out what I see happening, and this is mainly the motivation for my focus on open source. So if you look at open source silicon versus open source software, right? Obviously, the open source software world has been going gangbusters for years, and is completely reshaping the software industry. You compare that with what we are faced with hardware, and there are three fundamental differences between open source software and open source silicon, right? With open source silicon, to do silicon design, first of all, you actually have to have access to hardware to do your development, right? The open source community is not going to tape out an ASIC. That's certainly out of reach. There's actually a lot of focus in the open source movement toward open source access to ASICs. I think that focus is a little bit misguided. We've got FPGAs as well, and those are much more accessible. But still, even with FPGAs, you have to actually acquire that hardware. And that's an overhead, right? Any little overhead is an obstacle when you're talking about the scale of open source contributors. So you have to acquire the FPGA board. You have to configure that board and get it to work with your system to be able to talk to it.
Mm-hmm.
Whatever IP you're trying to run on that FPGA, you have to interface to it. And it's a lot of work to get that up and running.
Mm-hmm.
The next obstacle, to sort of map out the obstacles and then talk about where we stand against them. The second obstacle is access to the software, right? So this industry has traditionally been run by large EDA companies with very expensive software and very large, bulky software offerings.
Mm-hmm.
It's very difficult to get access to that software stack. Generally, you can do that through educational licenses and the like.
Mm-hmm.
But that can be a very real obstacle. And you have to get compatible software in many cases. The third obstacle is just that hardware is fundamentally different from software, and it's traditionally been very difficult to develop hardware. Generally, you need a higher level education to have the tools to be able to contribute to hardware, whereas software is much earlier in the educational process.
Right.
So looking at these three, what I realized a few years back is that the cloud providers were starting to provide FPGAs in their platforms. And if you have access on the cloud to FPGAs, you no longer have to worry about the access to hardware problem. You've got immediate access.
Still at a cost, but maybe lower than what you have to spend.
Yeah, it's a rental model, which makes it accessible versus the huge overheads of getting access to any decent performance FPGA hardware. So that addresses the access to hardware, and it's not just that you have access; it's the standardization of the platform. So if somebody develops an open source IP for that platform, they make it available to the world. The world has access to that same hardware platform. It takes away all the burden of configuring your particular platform. You just use the platform that the developer used. And software, these platforms are bundling the software on this same rental model. So you've got access to the software stacks. There's also all kinds of progress lately with open source EDA software. Very rapid progress in that space. And then the difficulty of hardware modeling is where all of my focus comes into play. Making it more accessible. As we did in this course that I mentioned, the students are able to learn it very quickly and get up to speed and do something real.
I see.
So realizing that my focus was playing into this third barrier, and that the industry was taking care of the other two. I began focusing in this space. I spent a good amount of time working with the cloud FPGAs and understanding that platform. Even though the platforms are available and in theory, they're breaking down the barriers, when you actually look at what the industry was offering, they kind of put the platforms in place and said, okay, we did it. You've got the software, but there was no ecosystem around it. It really didn't focus on that. And I wanted to incorporate these FPGAs into Makerchips so you could actually connect with these FPGAs. I haven't gotten there yet, but it'll be coming.
Right. I see.
So I built a framework.
This makes a lot of sense.
What's that?
This makes a lot of sense.
Yeah, I think it's really exciting. I mean, in general, it's a really exciting time to be part of our industry because so much is changing right now. I feel like for the bulk of my career working in CPU space, the industry was scaling, but not fundamentally transforming. And I think there's so much transformation sort of pent up and due to explode.
And I must congratulate the RISC-V ecosystem and the effort that's been ongoing, because I think a lot of this is driven by RISC-V.
It's phenomenal to see how strong a movement
it is.
That it has become just based on the fact that
you have an open standard,
right? There's no patent to it. Just that fact alone has been completely transformational.
True.
But so focusing on these FPGAs, I built a framework called First Class that enables easy access to the FPGA. Instead of a month to get the platform up and running, you can in 5 minutes be developing for these FPGAs.
Sounds very good. Very interesting. So tell me, so I think just looking at the clock and, a lot more to catch up on, but in the interest of time, might be interesting to wrap up for today.
Sure.
So if a listener who's listening to us today, you wanted to take off some 5 tips from you to become productive with their design verification, and what would be your 5 tips? So assume that some of your listeners are brand new, graduates, and a fair number of them are experienced professionals. so your tips would be interesting.
Yeah, I love, Ashish, that you wrap up your podcast this way. It's a great way to wrap up. I think my perspective, I haven't been focused on verification specifically since early in my career, so it's kind of funny to ask me about verification, but I think, the perspective that I bring to it is not so much about current methodologies and how to make them most efficient, but where the current methodologies are going to be limited and where we need to be looking for a future. So I guess the general theme to my 5 takeaways is to have a long-term view, right? Design projects tend to be very long projects. Obviously, it depends, if you're focused on a small IP, you might have a fairly short cycle. Mm-hmm. But generally, you're investing a great deal of time and energy into this work, and you really need to invest upfront in your verification methodology. So I guess, first tip, as we talked about before, use formal. It's very beneficial. Do some early path clearing with simulation and very quickly turn to formal. Mm-hmm. It's very easy to fall into simulation because it's understandable, it's easy. You know what you're feeding your device, you know what to expect in the waveform. But you have to keep in mind the fact that simulation is getting you incrementally closer to your target, whereas formal verification is reaching your target. Mm-hmm. So where you might not see the return as quickly, think about the long term and what's going to get you there fastest. Mm-hmm. So tip number 2, as a verification engineer, it's important to realize that you are fundamental to the success of your project. Mm-hmm. As we said, the verification is the bulk of the effort. I tend to see this, and not everywhere, but I have seen this sort of mentality of the architects define the big picture. The logic designers need to design within the constraints provided by the architects, and the verification engineers verify what the logic designers produce. It really shouldn't be viewed that linearly and like handoffs. Mm-hmm. You're part of the process. Your considerations for verification play into it. Every project I've been on, the management message is priorities. Number 1 is schedule. And if you can reduce schedule by defining a cleaner interface that simplifies the verification task, do it. It's the right trade-off. And hopefully your management is savvy enough to recognize that and supportive of the desire to simplify upfront. I would say most of the projects that I've been on, we always started off too aggressive. We paid the price of being too aggressive, and then we backed off. Recognize that up front. It'll make a big difference.
Very nice. I totally agree with that one. Yeah.
Let's see. Third, have the big picture in mind. Consider the life cycle of your models. Your model and the utility of your models is going to transform over the life cycle of your project. It's starting off with path clearing exercises and focus testing.
Think long term, basically.
Think long term and becoming random, and you're very likely going to need to have hardware emulation verification. I think hardware emulation and use of FPGAs is becoming increasingly important.
Indeed.
So planning upfront for modeling that can target hardware emulation is important, and that means your modeling should be synthesizable. It's actually one of the benefits of doing verification modeling in TL-Verilog is it's 100% synthesizable. And planning for this upfront and planning for post-silicon needs. So think about the use of your model in post-silicon. I'm not an expert with portable stimulus, but I know that that's a big focus with portable stimulus is being able to write verification collateral that can be retargeted and reused. Tip 4, again, not a UVM expert, but obviously UVM is the predominant verification methodology.
Mm-hmm.
And one thing I do understand quite well about UVM is that using a text editor and a command line prompts to develop UVM and debug with UVM is not going to cut it.
Mm-hmm.
It's very difficult to navigate around a complicated UVM model.
Mm-hmm.
And you need tools that are going to help you with that.
Mm-hmm.
These are not tools these aren't tools I'm going to offer. I'm not marketing myself here, but there's a tool called DVT from a company called Amic that I know good things about. I would certainly recommend that.
Okay.
You need to recognize as an engineer, there's no shame in using tools to help you. That's what you should be doing. I think there's sort of this mentality of the cowboy. I can
not invented
do
here.
It with,
not invented here syndrome.
That too. Tip 5, visibility into what your models are doing is extremely important. I've always, even early in my career, pushed on methodologies for being able to visualize what's happening in your designs.
Mm-hmm.
And surprisingly, that meets with resistance. It's sort of similar to this cowboy mentality of command line and text editor.
Mm-hmm.
People think visualization is a toy because it's not real functionality. It's an aid. Why do you need, but it's so important. You're going to spend so much of your life
reading something,
digging through simulation, trying to understand what's happening in the design. Invest a little bit in being able to understand it.
Indeed.
And I'll use this as a pitch for myself. This is a feature that I haven't released yet, but pretty soon I'll be announcing a feature called Visual Debug that you'll be able to use inside Makerchip to create custom visualization of your hardware model circuit behavior. So instead of turning straight to the waveform viewer and digging through things signal level, you can create a view the way you want to see it, right? Bring your documentation to life, be able to see how the hardware is behaving.
Nice.
At a high level. And then when your own custom visualization cuts out, you can turn to your waveform viewer and understand things at the signal level.
Very nice.
And we've been doing waveform debug for like 40 years. And
don't even get me started on that one. It's not something I'm a big fan of, but I can totally see why you're doing all of these things, Steve. And I would say it was a great chat today. I have certainly educated myself. I'm pretty sure a lot of our listeners not familiar with TL-Verilog today would be thinking, let's go and check it out. So thank you very much for your time. Thank you very much for your time.
Yeah, it was very nice to be on your podcast. I appreciate having the stage for a little bit, and getting to know you has certainly been a pleasure.
Oh, same here. So friends, keep tuned in. We'll be back next week. I hope you enjoyed today's podcast. Do check us out on our YouTube channel and email us at info@aximize.com. And we will be back shortly. Thank you very much.